till now we have been talking about a number of topics. We looked at data flow diagrams, we looked at structured English, we looked at decision tables, we also learnt about the fact that when you create data flow diagrams, you can create a data dictionary which is only a enumeration of all data which is used, and later on we looked at logical database design and how relational databases are organized or logically designed, and some aspects of so called database management system which primarily converts a logical database to a physical layout of the database or a physical device such as a hard disk. Okay. And all these tools and techniques which have been there for a number of years, starting possibly from the mid 60s, late 60s till even now, they are all called part of what is known as structured design. Structured design is something which was a technical term used for this technique of designing systems. And just like in programming languages, the early programming languages which looked at structured programming was Pascal, and later on C programming came into picture, which also was somewhat like a structured program, except that Pascal was somewhat easier to understand and C was a little bit more difficult, but C was a lot more efficient. And so the current trend is that we go towards what is known as object oriented design. Structured design has had a lot of, as I said, lot of use over the years, and even now I won't say that structured design is not used. It is used depending on the project. If it is a small project, you continue to use the structured design ideas, but there has been newer techniques which have come into the picture. Just like in programming, the structured programming ideas later on led to the so called object oriented programming methods, with primarily the use of C++ and Java. These two are so called object oriented programming languages. So the same algorithms were expressed now in an object oriented manner. There is object oriented programming languages was the vehicle for communication, and a lot of advantages are found in that. Similarly, in system design for businesses, there has been a movement towards object oriented system design. The reasons are several. Okay. One of the main reasons for movement towards object oriented design has been a recurrent problem in data processing or in information systems. The recurrent problems was that whenever a new project came, the new project was always started ab initio, and it does not use much of what transpired in the previous projects and so on. So whenever a lot of work and lots of programs were written for projects, and one would normally assume that all this which has been done could be in some way reused in the new projects, particularly because certain aspects of the old systems repeat, particularly if you are looking at, say, a class of applications like banking applications. If you have done one bank, then doing another bank should not be very difficult and should actually be able to use whatever is used for the earlier bank with some little modifications for the new bank. This is a kind of feeling people had. So number one is that one should be able to modify and reuse whatever is done earlier. Okay. And secondly, whenever you design a system, one would like to kind of componentize the design. What is meant by componentizing the design is that suppose you are able to come up with some self-contained modules, and those self-contained modules can be picked from a library of modules called component library, and use those components whenever a new problem comes along based on requirement specification. You find out what are the components from the component library you can pick up and put together to create this new system. Instead of having to go through and designing each module from scratch, it will be a very nice idea if you could use these components, and if necessary some small variations or small modifications of the components can be made, which is of course possible in a software system. This method of componentization, or using components to design a large system, from earlier experience has been the dream of all system designers, because that will have a lot of advantages, because the components which have been designed earlier have been used, and whatever bugs are there or errors are there must have been already found out. So, whatever component is being used is well tested, and so it will not hopefully bring in new errors. The only errors can come is in terms of interconnection of the components, but not within the components themselves. So, that is the advantage. This component is made efficient, hopefully, and made error free. So, you can just pick those components and use them together. So, it will expedite the project completion time, and time is money. So, it will also, that means it will also reduce the cost of designing a new system. This idea of using components is important when the complexity of the systems increase. When the complexity is low, one doesn't have to really worry too much. You can actually, for a low complexity system where the business rules are simple and where the requirements are not all that complicated, system you are designing is small, then all the structured methods you have been talking about are the ones which are relevant, which can continue to use it. Even apart from that, the structured methods really go towards also the componentization, and even in programming languages this idea of componentization has been with us right from the beginning of programming. In fact, in the early programming languages like Fortran, COBOL and C and so on, people have always talked about subroutines and functions. So, the functions effectively were thought of as components. So, you have a main program which calls all these functions for assistance and essentially strings together a set of functions, and the functions can be picked from a library of functions or subroutine library of subroutines, a library of subroutines. This has been of course the practice for design of large systems, where subroutines are well tested, to some extent generalizable and so on. But subroutines have a little bit of a problem in the sense that they are not data independent. In other words, there are some errors which can creep in if you don't pass the right type of data to it, and also the results of the subroutine, if the subroutine has side effects, in other words, if it kind of changes some aspects of the main program in some way, that can really lead to difficulties in debugging and so on. Okay. So, these are the problems which have been present with the idea of subroutine, but the idea of componentization has always been with us. Let me take one more analogy of componentization. In the area of hardware design, again, hardware have become continuously more complex. Today's personal computer, the entire personal computer, particularly motherboard, is fabricated in one board, and the success of the design of complex hardware has been brought about because of the componentization. Again, components there are memory is actually a chip. There is a chip called CPU chip. There are some chips which store or register a group of registers are in a chip, and so these are all well tested integrated circuits. Internally they will have thousands or even tens of thousands of transistors, and they will have been laid out, tested, produced in large numbers and so on, and so they are first of all become inexpensive. As the volume increases, the cost of the ICs come down. Like when a new microprocessor is introduced, it is expensive, but soon there are clones in the market, and the volume increases and the prices come down. And that is why in the hardware area prices have been coming down. In fact, the other way it has been happening, whereas the power of the computer has been doubling without the price going up. In other words, you get double the computing power in every 18 months without spending more money. That came about because of the fact that large scale components are used, and they are used to kind of put together on a printed circuit board a very complex system like a personal computer, like of fairly complex personal computer of today. Now, people have been looking at this, software people have been looking at this with some envy, saying that these guys are able to make components and reduce their cost and being able to improve their systems without increasing the price to the customer, whereas software costs are continuously going up because software is human intensive and human salaries are always going up from year to year because of inflation and so many other reasons. So, why not talk about software ICs as another way of looking at. These people said that componentization is equivalent to looking at a complex piece of software as a component. So, componentization or software ICs, can we talk about a software IC? And this is the trend which has led to the idea of object oriented programming first, and based on that we expanded to have object oriented modeling. In other words, when you do modeling of a system from the requirement specification, you model using objects. Just like in a database, we model using entities and attributes and relations, and we have a model of a logical database as a group of relations, and physically of course later on it is translated to a put in the hard disk. Similarly, model is something which is a logical model which uses ideas of so called componentization, the idea of reuse and so on, and becomes an actual you might say a part of a larger system. In other words, the whole idea of object-oriented modeling is that what are the components I am going to use, or in this case the components are going to be called objects. So, what are the objects which are going to be developed, and how can I make this the object fairly general purpose, you might say, and how do I know what the object can do, and how do I know when a full system is to be constructed, requirements SRS is given, that is system requirement specification is given, what objects to pick and how to kind of put together. These are all the part of the modeling. Once you do an object oriented modeling, then the next step is that use this model to now do an object oriented design, okay, which includes the programming aspects also. So, here you use an object oriented programming language for implementation. Okay. So, implementation issues come up in object oriented design, because design, even in systems analysis and design, analysis is modeling part and design is a part where you just implement. Similarly, database also, people are talking about object oriented database design, where the database, there are objects which are stored and objects can be retrieved and used and so on. It is just like having a library of objects. Okay. So, these are all being the trend. So, in the computer science curriculum, the object oriented design and object oriented programming is nowadays a very important part, just like DBMS is an important part of the curriculum. A whole course is normally devoted to object oriented programming, another course is devoted to object oriented design. Partly it is covered in software engineering courses and partly in a separate course called OO design, depends on the curriculum or the university where you take the course. So, in this course I cannot obviously look at the great detail the entire gamut of the object oriented analysis and design. That would really take us off to a different direction altogether. But what I would like to do is to be able to give you a flavor of what is object oriented modeling. So, the questions I am going to be asking in this module are, what are objects? First of all, we have to define what are objects, and why is it necessary to identify objects in application. Why is it necessary is essentially what I have been talking about all along, that is the idea of need for computer componentization and things like that. The motivation is very clear. Ultimately, once you are going towards object oriented modeling and object oriented design, hopefully the time for completion of projects will come down, the cost of completion of projects will come down, and companies can well tested systems well in time. So, these are the primary reasons why it is necessary. And how to identify objects given the system requirement specification, that is the most difficult or interesting part. So, given the system's requirement specification, how do I identify objects? And once I know what are objects, then I can talk about identification of the objects. So, then how objects are used to model an application. That is, after identifying objects, how to use them to model an application. So, these are the primary questions I am going to be asking, and as I said, in this probably at the most 2 or 3 lectures, I am giving you a bird's eye view or an overview of the object oriented modeling, and this is only something which will kind of make you understand why objects and make you also eager to learn more about objects and how to use them and so on. In today's world, when you go to in your regular job in the software industry, you are expected to be able to design using objects. So you should be fairly thorough with the subject when you get out of your engineering college curriculum. So the major impact of my talks are essentially to give you the, as I said, the basic foundation of object orientation. Okay, and that is what this is all about. Okay. Now, so to summarize, what I said is that the entire object oriented modeling is towards componentization and towards reuse and towards also reducing the cost and using ready-made components from a library to develop new projects. So the new systems, and so start effectively use all your well-tested components and so on. That is the whole idea. And so the learning units, of course, is objects and their properties, identify objects in application, modeling systems of the objects. That is what we are going to be looking at. And I said that information systems are becoming very complex. So we need methods to design complex systems. The main method is to break up a large system into a number of cooperating components and design each component or subsystem separately. Okay. And so the crux of the matter is the cooperating components. Each component can be designed independently, but you should be able to cooperate. In order to cooperate, they need some properties. They must have some properties. So those properties are the important properties which will distinguish an object from say a subroutine or a function. Okay. So the best what is the best method of designing, or you might say breaking up a system into components which can cooperate. There is each one can use the services of the other. So how do we do this? The main purpose of this module is to answer this question. Let me take an analogy of the general idea of cooperating components and the use of libraries and so on. It's a very mundane example, in other words, day-to-day example. Nowadays, when people want to have a marriage conducted, the marriage conduction, it's a very complex affair, the organization of marriage, okay, because you have to do a hiring of a hall, you have to kind of get the proper food served at the proper time, you have to print the invitations, and you got to have the proper type of proper methods of arranging for reception and so on. There is a whole lot of small details one has to go through, lighting and God knows what. There are so many items, flowers which are required and so on. Nowadays, people don't do that all by themselves from scratch. They use, you might say, cooperating agents. Each agent does a bit of a job. Like for instance, if you want to kind of give proper meals and so on, you get out of a caterer. The caterer's job is to provide the food at the right time and so on. So what the caterer does is to give you a set of menus for various parts, like for instance breakfast menu, lunch menu, dinner menu, tea menu and so on. And then he gives you a choice of menus, and you pick the cost associated with each menu. So you decide on which menu you want to use based on your budget. Then based on this menu which has been selected by you, you tell the marriage the caterer how many hours are expected for each of the meals, breakfast this many, lunch this many, dinner this many, and so on. The number may vary. Then people who may take breakfast may be much smaller than people who take dinner. Okay. So you make an estimate of the number, and you also tell the caterer plus or minus some, and whatever is to be done, he has to be able to, if more people come, he still has to kind of be able to cater. So once you give this order to the caterer, you don't interfere with that caterer anymore. The job has been assigned to the caterer, and you expect the caterer to deliver as per your requirements. So it's a subcontract which has been given. Similarly, you can give a subcontract for the marriage hall. You give a subcontract for the flowers to be given, what type of flowers, when, and so on. So the question is, the number of many contractors, each contractor has got a specific job, and the contractors have to some extent cooperate, particularly in terms of timings and so on. Certain things have to happen at the right time, and so the conduction, the project or the project of conducting a marriage is simplified by giving the complex job of conducting a marriage has been simplified by giving contracts to several contractors who cooperate to get your work done at whatever cost you already decided on your budget. So we can be within the budget, within what you require, and you essentially are giving orders and not interfering with those afterwards. Similarly, in the area of objects, you might think of objects or components as contractors. The contractors have been given some contract to do some job, and they are self-contained to do that job. In other words, they know what methods to use to get the job done, what data to use to get the job done. Just similar to a caterer. A caterer once gives you a menu, the method of cooking you don't tell him. The method he knows, the best method of cooking. He knows what items are required to be purchased from the market to have the menu prepared for the number of people who are told. So in that case, the items are like your data. So data is kind of, he has encapsulated, you might say, the requirements, required data. He encapsulated the method of doing this job, and the only thing you do is to give an order. And when you give an order to carry out, then he uses his own methods, and he uses his own component, he uses his own data to deliver some output, and that's essentially what object oriented is somewhat, it's analogous to that. So one way of looking at object oriented modeling, that how to pick subcontractors and how to kind of make the subcontractors cooperate to get a large job done. So that is a primary, if you keep that kind of analogy in mind, then modeling becomes somewhat simple. In other words, you should be able to kind of do this, you might say, we use of course technical terms like encapsulation, we talk about polymorphism, inheritance and so on, but these are all somewhat have analogies in terms of real world items. But we will describe or talk about these aspects like polymorphism, which are very specific to the object oriented modeling world. Okay, these you might say jargon terms or terminologies are always used, but of course they got a meaning, they have a purpose. Okay, so the main purpose of this module is to answer the question, how do we componentize an object and use them. So each subsystem or component has a clearly defined responsibility, just like a caterer has a clearly defined responsibility. Acts when requested by an order. So, you give an order to the caterer, he will produce the items you require. How the component does the work or task need not be known to you or to other components. That is, it is self-contained. In other words, how the caterer is going to cater to the number of people need not be known to the person who is going to serve, give the flowers and so on. He does it independently. Okay, and he need not know. So there could be cooperating components which may have to know. Like for instance, suppose the food has to be served at a particular time, the marriage hall people must be ready to provide you the tables and chairs and arrange them appropriately at the right time to cater. So caterer, that marriage hall person has to cooperate with the caterer to be able to provide the number of chairs, tables and so on required for each meal. So he essentially requests the another contractor, namely the marriage hall person, to do it. So these two have to cooperate. What the component does, of course, should be known. I mean, in the case of caterer, you know that caterer is supposed to prepare meals as per your menu for a certain number of people. Component which is general enough to be reusable. Okay, that is, in other words, no contractor of the name will be able to survive unless he has a method of cooking several menus. Method for several, if he can give only one menu, one customer may not like it. So there are several customers, so each customer may have specific requirement. So the person must have enough menus and must employ cooks and have methods or recipes which is general enough to be reusable. In other words, he should be able to kind of use the same cooks and the same vessels and so on which he has to be able to cater to many different customers with many different requirements, with many different number of people who may take the dinner and stuff like that. See, so it is general enough to be reusable. Variety of components should be reduced. This is facilitated by allowing components to inherit properties of other components. This is somewhat specific. In other words, the variety should be reduced in the sense that one component should be able to do a fairly number of different things. So versatility of the component is important. Like in the caterer, if the caterer says, I can only prepare breakfast and I am not good at preparing dinner, you would go to another caterer who is general and who's got it's not a very good analogy, because the inherit properties of other components, the sense that you should be able to inherit the properties of another caterer who does good North Indian food, you might say. Because suppose a person wants North Indian food to be given for dinner, then the properties of those recipes which are required should be able to inherit or be taken by this. In other words, should be able to generalize. Of course, I am taking an example which is not really directly relevant to data processing, but this brings out the ideas, and now of course I look at specific examples in data processing also. Another way to generalization of functions, because I think the key idea is generalization, and also there is something called specialization. We will come to that. Another way to generalize functions of a component is to allow generic commands which make components do that task. When I mean talk about generic commands, there is we will look at that in very detail later on. Like when you say admit, the admit in the case of a system in a college would be to admit a student. In the case of a hospital, when you say admit, it may be as admitting a patient. So if suppose the admission process is a component which is general enough to cater to either of these two, when you give admit in a hospital context, you should be able to use appropriate methods. And if you give admit in the case of a college, you must use the appropriate methods. So that is what is meant by generalization. This is called polymorphism. See, in other words, it is able to kind of have different avatars for different purposes. Okay. So object-oriented modeling is your component-oriented design. Facilitates changes in the system at low cost, mainly because the components are all, suppose some changes is required. I have been saying right from the beginning of this course that one of the most important aspects of system design, particularly software system design, is design for change. In other words, you always have to design for change and not design for stability or permanence. When you have to design for change, then if you use components and a change requirement comes along, you may be able to change certain components only, and other components can be left untouched. Okay. To give an example of what I mean by this is that suppose in a college you have a component or an object whose purpose is for, say, collecting fees. Another object may be having the purpose of creating the mark sheet. Okay. So suppose the fee structure is changed. So the object which does the fee calculation is the only one to touch. As far as the examination and marks and creating a mark sheet is concerned, that component is left untouched. So any change in requirements has to be met. That means when you pick components also, you have to pick components in such a way that they have some orthogonal purpose. So when requirement of change arises, you can just change some of the components and not meddle with the other components. Okay. So the whole idea is the fact that change can be implemented at low cost. Promotes reuse of components. So reuse, of course, I have been talking about the importance of reuse. Whatever you did for an earlier project should again be usable in a new project. Process of integrating components to configure large systems is simplified. Okay. And by the kind of models and by the kind of properties which objects have. It also simplifies the design of distributed systems. In other words, what I mean by distributed systems, question of what is a distributed system? Nowadays, if you look at a computer, no computer is a self-contained box sitting alone. Number of computers are connected together by either local area network or the internet or whatever. In other words, the isolated computer doesn't anymore exist. Every computer seems to be connected to every other computer. Sometimes every other computer in the world. For instance, in your home PC, when you connect to internet through an internet service provider, you are automatically becoming a part of a worldwide network. So you are connected to the whole world. You don't know that, but you are connected. Virtually you are connected, you might say, through the internet service provider, because the internet is a network of networks, and network of networks are all international networks. Otherwise we can't be going through the web and things like that. So the point is that no machine is an isolated machine, and so a distributed computer means that you have a number of different servers which cooperate to get the job done. Like you might have in a local area network, in any college, there will be one computer which will be a printer server. There will be another computer which will be a storage server. A third server may be a number crunching server, and a fourth server may be for communications and so on. So also you distribute jobs to these servers for load balancing. You don't want to overload a particular server, and you would like to balance. So this kind of load balancing and distributing tasks becomes simple if you have some kind of a component, because different components can be assigned to different processors or servers, and they can cooperate with one another to get the job done. What can we model as objects? All tangible entities can be, an application can be normally modeled as objects. A student, because these are tangible, means it exists as a animate or inanimate being. A student, a cycle, a train ticket, a vendor, an item, okay, an order. So these are all actually entities. You might say these are tangible entities. Okay, tangible in the sense that a vendor has got an address and he exists. An item is something which is physical. An order is something with a number, and there is certain kind of just like a train ticket is an order, is something which you place an order with a document. Okay, and there are also intangible entities like a bank account, stat data structure, or insurance policy, and stuff like that. And to some extent, the order is somewhere in between. An order can be thought of as intangible from that point of view, because order, unlike a vendor, order is not a physical entity. It's a kind of a logical entity. Like for instance, whereas train ticket is more of a physical entity because you can hold a train ticket in your hand. That's the reason why order also is something which you can hold in your hand. To that extent, it is you might say a tangible entity. Okay, but data structure is something which is clearly an intangible item, but doesn't really matter. Okay, objects with similar meanings and purpose are grouped as a class. Like for instance, a student is an object. Okay, a student, say for instance, student for instance is an entity, but if a class of students together have similar properties. Students are a class, and so so it's called a class. There is objects with similar meanings and purpose are grouped together and are called a class. A member of a class is an object instance. See, in other words, I want to make the distinction between objects and object instance. Object instance is a specific, one particular kind of an existence of an object. Okay, whereas the object is generalized. It's a general idea. Instance is a particular case of an object. Like a particular student is an object instance, whereas a class of students is an object class. All objects have attributes. Okay, attributes, just like entities attribute kind of a thing. Object itself is a kind of an entity, you might say, and it's got attributes like student has a name, roll number, year of admission, department. There will be other attributes also, like if you are hostel resident, hostel number, and local guardian, and so on. So a number of attributes of an object depends upon the application to which you want to put. In other words, you should have a fairly general set of entities, a large number of entities corresponding to an object class to be able to do a number of different things with the object. To that extent, I think what should be, I think it's a question of art, to some extent it is not really a science, in the sense that you can't have a strict rule saying that an object cannot have more than 7 attributes, or but you normally have a certain number of attributes which are relevant to the application. All objects have a state. That is important. State is that state of, for instance, a ticket, an object like a ticket has a state like reserved or waste. A student has present or absent, or student, if it is a examination kind of a thing, student state may be passed or wait or not passed or deferred. An admission process, a student may be admitted, waitlisted, or kept pending. So these are of course are not admitted. So these are all states, and so each object will have states which will change as per the context. All objects have a set of operations which can be performed on them. Admit a student, cancel a ticket. See, now the operations, when you say admit a student, cancel a ticket and so on, when you do the implementation of that operation, the implementation is done by some program. This program which does the implementation of the operation is normally called in the object-oriented context a method. The method, of course, the method implementing some algorithm or a method of admitting or set of rules, business rules for admitting. So the business rules are being incorporated in that. So the methods are essentially part of the object. So this is called encapsulation. The method is encapsulated within the object. And you invoke the method by sending out a request to the object to invoke the method. So you send a message or an order. The order gets implemented by means of the method which is inside the object. So this is a major difference between the idea of a subroutine or functions and the idea of an object. Object has both general methods as well as data on which the methods act, all encapsulated within a, you might say, sealed boundaries, and it doesn't depend on data from outside. It's self-contained. So you only send a trigger or an order and the object gets activated using whatever object data is required is encapsulated within it. Unlike a subroutine where some data may be global, some may be local, and so this is where it leads to all kinds of problems because data is not really encapsulated. In this case, data is encapsulated. The method again operations which require the data is also encapsulated. You only give a trigger to for this. There is something called a universal modeling language which has been designed by 3 stalwarts in the area of object-oriented modeling, Booch and 2 other people, I don't remember their name, and there are 3 people who really cooperated. Each one had a different method, and ultimately they thought that it's better to standardize by cooperation, and so they cooperated to come up with a universal modeling language which has notation for classes, objects, entities, attributes, operations, and so on. Okay? And also has got many other parts. So UML is a very complex modeling language. Like a data flow diagram and data modeling, object modeling is normally done nowadays with a UML modeling tool. In this particular set of lectures, I am not going to look at UML at great lengths, for a simple reason that a whole books have been written on UML. And in order to deeply study UML, we have to go through those books, and normally it will be taught in object-oriented design course, which will follow this course. And so you should really understand this kind of flavor of what UML looks like. So I am not going to talk about UML at a very great length, for a simple reason it is outside the scope of this particular course. This course is a very broad-based, you might say, a foundation course on which you build the rest of the computer science curriculum. It comes early in the curriculum for you to understand. Okay. So the UML notation for a class is there is a class name. In the case of, say for instance, I am taking a vendor. Vendor has got a vendor ID, vendor name, vendor address, vendor type. I am just taking some attributes, there will be other attributes depending upon the application. And there are operations or methods. See, there are methods essentially means that they are algorithms encapsulated within that class. See, so add vendor, delete vendor, find address, change address, find vendor type, all these things which will operate on the attributes which are already stored internally. See, we have been looking at database design earlier. In database design, when you do a logical entity attribute modeling, they come up with relations. The relations only talked about the data. They didn't talk about any kind of method which will operate in the data. In fact, the coming of the object-oriented system partly came out of the work which is done by database people, partly out of the work which is done by the AI people in terms of agents and so-called software agents and so on, and so also programming people. So it kind of many of the disciplines together cooperated in terms of coming up with this general structure. So it is actually using the ideas from all these and hopefully better ideas from all these to get to a system which is hopefully going to last longer than what others lasted. I mean, of course, I can never predict in computer science. Things change so rapidly. But I think it is the change is brought about by the fact that we are very young field and we are always trying to improve and improve our productivity, reduce our cost and so on. And in that process, we are always trying to find out better and better methods, which is only a good thing, because that way, as a software engineer working in the field, you will always I hope that you will always try to find out what are the latest trends, keep in touch and learn as you go along, because learning is in our area you have to be continuously learning, and things change, and as things change you got to continuously learn the new changes which happen. Actual values and attributes when you give, it becomes an object instance. So object instance of this object is say vendor ID, say object name and its class name. See, when vendor ID is specifically about, because you want to kind of talk about a specific vendor when you do an operation. Okay, vendor ID and the class name, and vendor, see, these are all actual values of the attribute. There is vendor name, vendor type, vendor address, whatever attributes are there, the values of those attributes. Okay, and so the actual values are in object instance. Constructor is a operation types on objects. What kind of operations on objects can I perform? Constructor is creating a new instance of a class, deleting existing instance of a class. For instance, add a new vendor. Okay, and in other words, I should really say that I'm updating, you might say, putting a new instance or deleting existing instance. In other words, suppose nothing remains static. If I got a vendor list, I may have a vendor list today, and I would like to kind of, if a particular vendor is not performed very well, I would like to delete that vendor. If a new vendor has come into the market, I would like to add that vendor and try him out. So deleting an existing instance and adding a new one gives a constructor, and a query is accessing state without changing the value. Okay, so there is no side effects. Like for instance, a query is what is the vendor address. So vendor address is found out by just looking at what is already stored. So data is stored, and so it is data independent. So data independence is one of the most important parts of any object-oriented design. So I need to have data independence. So a query accesses a state without changing any value, has no side effects. Like some subroutines have side effects. Change values of one or more attributes. Update affects state of object, has side effects. So change of address of a vendor. Okay, it's a requirement. Now the vendor's address is changed. Hopefully outside the object there is no effect. So only internally that I have changed the address, and the address change gets reflected in whatever method I use in that object. Okay. Implementation operation objects called methods, which because I already used the terminology called methods. Implementation, there is any algorithm to implement an operation is called a method in the object-oriented context. New classes are created. Inheritance is a very interesting and important idea. The reason why inheritance is an important idea is that whenever there is a new application which comes along, I want to use some of the objects already created in the old application. I would like to be able to use that and create a new object which inherits some of the properties of the earlier object. So new classes are created from existing or current classes using idea of inheritance. New classes inherit attributes and are operating with existing classes. Inheritance allows both generalization and specialization in modeling. Specialization in the sense that I will be able to kind of take out some of the methods maybe and make it specialized, or make it more general by adding more methods, but data is encapsulated and so on. So inheritance is an important idea. Specialization gives to I will talk about inheritance and specialization at much greater length next time, because these are important ideas to be discussed. So I don't want to rush through with this. So next time we will start with this inheritance idea and go further.